Hello everyone, I'm Haofan from Huazhong University of Science and Technology. This paper introduces GEAR, a new on-demand image format for container. Here is the outline. Let's begin with the background. Containers are becoming more and more popular. It can provide a lightweight and isolated runtime environment by cgroup and namespace. And all things required to run the application are packed in a layered image, which makes deploying and updating the containerized application convenient. However, when containers are big, deploying an application with container is slow, because we need to spend a long time on downloading images. Moreover, storing the images are expensive for registry. For an image, substantial unused and redundant data are downloaded to deploy a container. One of the ways to reduce unused and redundant data is designing on-demand remote image formats. However, existing methods have the following disadvantages. A file system-based remote image usually adheres to a specific file system, like NFS and CFS. Some desirable features of popular file systems are missing for NFS and CFS. A block-based remote image needs to build a virtual block device for each container. The size of virtual block device can't be adjusted according to the actual sizes of images. Furthermore, existing remote image formats require significant modifications in I/O-stack, like designing new storage drivers. This holds back the widespread of these methods. In addition, existing methods do not support local cache. Accordingly, we designed GEAR. GEAR mainly solves the following four issues. First, solve compatibility and flexibility. Second, enable file-level sharing in registry and client. Third, deploy a container based on GEAR image. Finally, handle modifications. First, we convert an Docker image to a GEAR image by decoupling the metadata and regular fields of Docker image, and store them as GEAR index and GEAR files respectively. GEAR index is made up of metadata that contains the structure of the entire directory tree, and indexes of regular fields which replace the actual fields in directories. Regular files are converted to GEAR files by naming them by their fingerprints. When we need to access a file, we first find its fingerprint in the GEAR index based on its file path. Then we can find the GEAR file through its fingerprint. The GEAR index is stored in a single-layered Docker image. In this way, we can download the GEAR index to client with the original Docker commands. After GEAR index is downloaded, we start the container with GEAR index and access GEAR index with existing I/O-stack. Then the GEAR files are lazily downloaded when they are required, based on the fingerprints in GEAR index. Next, we realize file-level sharing in both registry and client host. In client host, we build a three-layered storage pool. GEAR files are stored in the first layer. The second layer saves GEAR indexes. In the GEAR registry, all GEAR files are stored in a storage pool, and GEAR indexes are stored in Docker registry. In the local cache and storage pool, files can be identified by their names, because only two identical files have the same fingerprint. Accordingly, we only store files with different names to eliminate identical files. It takes 3 steps to deploy a container based on GEAR image. First, GEAR pulls GEAR index from GEAR registry. Second, GEAR finds GEAR files in local cache based on fingerprints in GEAR index. Third, if the GEAR files are not in local cache, GEAR turns to storage pool in GEAR registry to get them. Original GEAR index and GEAR files in local cache can't be modified. because they are shared by other containers. Accordingly, we create a directory named diff for a container to hold the modifications. When we need to modify file f1 in gear image, we create a file f1 in diff. The modifications of f1 are carried out on this file. If we want to commit the container as an image, gear first instructs the file's contents in diff to construct gear files and then store them to local cache. Finally, gear combines the metadata of newly added files with the gear index of current image to build a new gear index. Next part is our evaluation. We build private registries with gear and Docker separately. We store latest 20 versions of top 50 popular container images from Docker Hub. Gear registry can save 54% of storage space compared to Docker registry's layer-level sharing. Next, we deploy the images on client hosts one by one with Docker, gear without local cache, and gear with local cache separately. When the bandwidth is 1000 Mbps, gear without a local cache improves the deployment time by 1.4 times on average, and gear with a local cache improves the deployment time by 1.6 times on average. With lower bandwidth, gear achieves better performance improvement compared with Docker. This means gear is suitable for bandwidth-limited scenarios, such as edge computing and the Internet of Things. Finally, we conclude our paper as follows. In this paper, we propose gear, a new image format that supports on-demand download of image data based on existing IO-stack. Gear can save 54% of storage space in registry and speeds up deployment time up to 5 times. That's all for the introduction of gear. Thanks a lot for your attention, and any questions are welcome.